And with my eye, you could just focus. They're very. You see that? They gotta send it to the
Last time I was told, hey,
My Yuchi is the best way I can work with.
There must be a big.
No,
No.
Oh, yeah, they got it. How do, sorry, such a huge.
that's sort of me. I don't know if they show up with these parts. You might not see all that.
Okay, it's 7:30 and we're going to get started. It's 7:30 and we're going to get started. Okay. All right, so welcome to the November meeting of the Johnson Space Center Astronomical Society. Before we get started here, our opening slide has a picture from Stan. And Stan, would you like to tell us a little bit about your picture?
Yeah, so first it's molecular cloud, so about 6 degrees by 2 degrees for the field of view. The image out there was only like 5.5 by 3.5, so I didn't get the whole extent of it. But what I've read is about 1,000 light years away from Earth, and it's 500 light years in diameter. And it's a star-forming region. There's 2 clusters. On the left is JSC 348, and on the right is NGC 1333, and they're both star-forming regions as well. And from what I've read, there are like over 60% of the stars have total planetary distance.
Excellent. All right, thank you, Stan. Great picture. It's a very interesting area. Here's our agenda for this evening. Before we get started, we'd like to welcome anyone who this is your first time here. If it's your first time here, raise your hand, tell us your name, how you found out about the JSC Astronomical Society, and what your interest is in astronomy. Right there.
Hi, everyone. My name is Kate. This is my first time into this location of the village, and also join this. This type of event here. But I joined some other event in Rice, and I'm interested in watching the stars. And also last year I joined the solar eclipse event.
Excellent. Well, we're glad you're here. Anybody else first time here? Anybody else that's willing to admit it's your first time here? Okay, good enough. All righty, this is our agenda, and we have email distribution. If you'd like to get on our email distribution, you can send David a note here at starhopper457@gmail.com. If you can't get that copy down, there's some tear off tabs up there. I think did I put the clipboard up there?
No, we don't have the.
Okay, I will put the clipboard up there later, and you can get a tear off tab with the email address on if you want. My apologies. Reminders to presenters, mainly you, Dr. Masood. Okay, so the pointer is a mouse pointer here. It's built into the computer. We use this so that people online can see what you're pointing at. The stream mic is in this computer. You know, the auditorium mic is here, so you can't go very far away from this area right here, or the people online can't hear you. So just be aware of that. I feel like I'm forgetting something. I don't know what it is. Anyway, so what? Oh, yes. Okay, so there was a comment about that during the meeting, some people are playing sounds on their phones. It makes it hard for the people next to you to hear what's going on. So please don't play any kind of sounds on your phone during the meeting. Thank you. All righty. Tonight, our main speaker is Dr. Samina Masood with Astrobiology, Biology in Space. Before Dr. Masood comes up here, let me tell you a little bit about her. Dr. Samina S. Masood is a physics professor and a program director at the University of Houston Clear Lake, UHCL, where she studies how the universe works at its most fundamental level. She earned her PhD in physics from the Quaid-e-Azam University in Islamabad, Pakistan, focusing on how particles behave in extremely hot and dense environments like those found in stars or the early universe. This work laid the foundation for her lifelong interest in space, matter, and the forces that shape the cosmos. She joined UHCL in 2006 and gradually expanded her research into biology, inspired by how the same mathematical tools used in physics could help explain how molecules behave in living systems. This led her to explore how quantum mechanics, the science of very small systems, can be applied to things like cell growth and genetic changes. Dr. Masood has written over 100 scientific papers, which are widely cited for her work in areas like how particles change in extreme environments like stars or the early universe, and how invisible quantum forces affect tiny structures like in nanotechnology, and how weak nuclear forces shape the formation of elements, and how particles move in strong magnetic fields like in neutron stars, and lastly, how magnetic fields might influence living cells and DNA. She has published in respected international journals and written 2 books on quantum electrodynamics, the theory of how light and matter interact, one published in 2014 and the other on the way in 2025. So join me in welcoming Dr. Samina Masood.
Okay, so I will be moving here. Okay. Okay, thank you for the introduction, but I really don't know if I'm all that. That's all I will say. Okay, so, I'm sorry. I was about to use this one. I'm so much used to use this keyboard. No, that's okay. Okay, so this is actually a picture of DNA, and I'm sure most of you have heard the name DNA. So this is basically, it is kind of RNA, which you can find in single cell creatures like bacteria and things like that. But DNA is in multicellular animals and big objects. Anyway, so here I will talk more about questions than answers, that what is really meant by the study of biology in space. Of course, biology looks like that we are looking at something which we can really see, feel, and all that. But when it comes to space, everything is almost virtual. We cannot go anywhere, maybe further than a plane, and we can really see anything in detail. So all the information which comes to us is through radiation or light, basically. So I will talk about it a little bit more. However, when we talk about life, that there are certain questions which we don't know. So first of all, we want to see, are we alone in the universe? We as life, intelligent life. Then the question comes, okay, maybe not intelligent life, maybe life in general is life only available, is there on Earth, or there are other places also? When we go for the search of life, there are different type of things which we can look at it. One of them is, we call it extraterrestrial life, but one of them is, can we find any other place where there are some traces of life within the solar system? Of course, we are part of solar system, so life started on Earth. So it means the same material should be found somewhere else, and that material may be should be organic material, which is responsible for life. Then, for that purpose, we look for life on planets, satellites, or wherever we can think about, even on asteroids and other places. So for that purpose, we use the information about planetary atmosphere, planetary geology, and those things. Is it possible that life can exist on these places or not? So this is one of the ways to look at it. Second thing is a little bit more applicable or more understandable, that since we are working a lot on sending humans in space and we are thinking about it, so for that purpose, we want to see what we should expect in space. Are we going to find the same type of environment in space, or it is something different? So for that purpose, we study the radiation in space. Then if there is radiation there, and since life is not everywhere else, so we have a lot of study on the radiations on Earth. So we know that how the radiation can damage. Now when we talk about damage of radiation, we mean high energy radiation, and these high energy radiations are those radiations which can ionize atoms. What it means is that when this radiation interact with the atoms or molecules, they can knock out an electron out of it or something, or break bonds. So that ionization damages radiation. On the other hand, we all are aware of this right from the beginning of life, that radiation is needed for the survival of life. Even if you must have noticed during the solar eclipse, if sun is eclipsed for a few minutes, right away you see the temperature difference. So if there is no sun for one day, think about it, maybe everybody will die due to some reason. So that is something that we know, that radiation is essential for the survival of life. And on the other hand, radiation is extremely dangerous for the survival of life. So we have to find out what is the difference. Now, considering all these facts, we want to see what happens when astronauts are sent in space, what they will come across, how to protect them, and all those type of things. These are all known things actually for the space mission. Actually, there is something is messed up in my first slide, so I'm sorry about it. So now I'm going to go on stepwise. When we go to extraterrestrial life, then a few candidates of life. This is not actually candidate. This is our Earth, and we know life is here. Then we look at Mars. Is there any signatures of life on Mars? We know, we have been talking about all these things a lot. Then Moon. Is there any signature of life on Moon? That maybe there was some life earlier which was destroyed or damaged for some reason. Then there are a few other satellites like Europa, Titan, and other satellites, or which we call planets, moons also. They may have life. Now here I want to talk about one thing, that there is a kind of background information about the solar system, that it has probably come up from the explosion of supernova. So when supernova explodes, it is producing a lot of pressure, and due to extremely high pressure, when supernova explodes, large elements can be produced, which we don't expect in the early universe at all. So those elements And this theory is because of the reason we see heavy elements here like uranium and plutonium and those kind of very heavy elements. So the presence of heavy elements indicates that we are produced after the supernova explosion. If those elements on Earth have produced life, why it is only available here and nowhere else? Then we talk to biologists and chemists and we come to know that it is due to the presence of water, oxygen, and some of the other things which are needed for the survival of life. That's good to know, and we want to understand that why still we are alone. Because within the solar system, we can have some more information. It is still kind of indirectly within the scope of our study. So, however, we could not succeed to get really good information about uh, existence of life. There could be traces of life, and we know that there is a possibility that some time ago their life was there, but we are not sure. But this is still like within discussion range. We are talking about it. Now, the next thing is, if there is life, what we expect? Of course, if there is an intelligent life, if we are looking at other planets and other systems, then intelligent life may be able to communicate with us, but we don't see that. So we look at basically what is more considered is the possibility of life, which is basically small scale, like bacteria, virus, and fungi. I don't remember exactly which year, but a long time ago, during the Mars mission, they thought that we found bacteria from there, and then afterwards it was figured out no, this bacteria actually traveled from Earth and came back. So the reason why I brought that up is that fungi, fungus, bacteria, virus, they're all kind of single cell creature forms of life. There is a possibility that this kind of life may be possibly able to find somewhere else because of the what we know about the existing condition. Other lives cannot survive. Then there are some very interesting animals, organisms, which we can see. They are, oh, what happened? Sorry. Okay, one thing they think is that if it is pressed in between some rocks or something, it may be kind of damaged and we may not be able to see the actual structure, and there could be something like this. So I have a small video here. Let's see if it plays.
No, it's not gonna work.
It won't do that? Okay. So this is something I just put it here. It's a YouTube video which shows that how you can see small creatures inside a drop of water. And looks like that there is a whole world there. Like worms and big animals and not animals, of course, that is microscopic pictures. Okay, so based on that, now we are talking about, this is a very big topic. So today, since I think we are talking about this thing for the first time, so I'm more like going to give you some information or what is really discussed in this subject. So, of course, astrobiology means biology in space. Now, what is life? How we define life? Life is basically our definition of life, or what we call life is something which is basically what we call carbon based life. Carbon is an element which is very different in nature, in behavior from all the other elements in the periodic table. Carbon is the only element which can make a chain. And I have pictures of that. That 6 carbon atoms can combine together. They make a chain and they make a hexagonal structure. And they have 6 bonds, 5 bonds which are at the place. And the other 3 bonds can be at one place in one form or the other form. There are 2 isomorphic forms or just like 2 forms available, and out of those it can be anything, and that is basically that chain, that carbon structure is required for the existence of life. Every single organic molecule should have that carbon chain, not one, the whole line. All the polymers, all the DNA or other protein structures and everything, they're long chains of carbon uh, structure, and those chains are, they are all folded together, and they are microscopic, very small. You cannot see them as small molecule, but if you open the chain, they are meters long chain, which are all folded together to give you very small molecular structures in the body. All our stem cells and like the DNA and genes and everything is like this. Yeah, this one I was looking for. They look like big creatures, but they are all microscopic creatures. I don't know, somehow my picture moved there. So, in addition to bacteria, fungi, and virus, this is called tardigrade. This is also called sea animal, sea elephant. Sorry. This is protozoa. There are all different type of things. I just showed it so that you can have an idea. Amoeba is also pretty well known because there's amoebic dysentery and other things. So that is pretty commonly found. So all these organisms are expected to be surviving there. Okay, so this is the carbon chain I am talking about. So this carbon chain, like here, it has 1, 2, 3. This 3, I have no way to answer this question. If one of you asked this question, why this is 3 and not 1 here, 1 here, and 1 here? There is equal probability that carbon chain could be in both ways. So due to that reason, it makes a structure which is basically changes very quick, easily. I am not actually a biologist. I just have undergrad biology knowledge. But still, this is something which suggests that probably this property, which is a very unique property of carbon, is playing a big role in the reproduction of cells or protein molecules or growth of life, automatic growth. So this is how it works. So there is another very interesting thing about life, because I'm talking more about human life or big animals life. There are only 4 basic elements like these type of thing. These are 4 of the molecules of amino acids, which are basic building block of DNA. Those 4 elements, just like computer bytes or bits or qubits, you can call it qubits for byte structure, they create all the variety of human being. 96% of coding of DNA is same, no variety. Only 4% is variation, which can create variety, and that is how we are all so different looking people with all different backgrounds. So that is something which is pretty amazing, and this is how kind of coding takes place. These are the 4 basic building blocks, and they can have like these diagrams are pretty complicated. I just wanted to show you just to give you an idea, but they are like different type of codes. And I think, I don't know for sure, but I think that is something when they do the DNA testing, that code actually indicates actually. If somebody else is working in more bioscience, may be able to answer that code is actually red, and that code indicates that this is the correct DNA or not. But that's only 4% of all the DNA structures. Now we are this is one part of the information which we use for the space biology. Now the rest of it is the other part is when we look at the space travel, we want to see that can we, this is more practical part of space biology. By the way, if anybody has any question, please feel free to interrupt in between. That's not a problem. So when it comes to space travel, people, when human beings go out, the biggest concern we have is human beings are used to live on earth. Actually, it is up to that level that if you are coming from a hot area, hot country, or hot area in the same country, and come to the cold area, you will feel more colder, more, and you need more stuff to protect your body. And if you are going from cold to hot area, you will feel hotter. So we human body, actually it's not only human body, life is so much used to get adopted to the environment that it is very important that the how we define the habitable place. We cannot, we don't like to have too much difference of uh, environment. So for that purpose, we want to see, is it possible that human can really survive when they are traveling? So moon travel is, of course, it is important, and since it has been achieved, so we are not, we think that we understand how to handle it. But when it comes to long time travel, it will take long time to go to Mars. It is not very easy to handle that. It will be a long time in space, and we are facing so many challenges how the life can survive there. Then, is it possible that if the environment over there is not habitable, is there a way that we can create a habitable environment manually ourselves? And if that is the thing we are used to here, we need every time when we take food, we want some variety. So, can we produce some variety? And for that purpose, can we provide some fresh vegetables or something, fruit or something in space? It looks like a dream right now, but that is something which is a concern, because if astronauts travel for like 6 months, can they survive totally with the preserved food, or they need something more than that? That we can create a way, we can find a way to grow some edible in space. So that is also a concern. Then, if the bacteria or some other contaminating things are there, because it is always possible, then what will happen to that? Can we control it? Can we? This is important. Bacteria is extremely important to understand if we can protect our food, like astronauts' food, for a long time, for 6 months. We have to see, can we protect food easily? Can we do those things? So I know a lot of this work is done, but it is still not enough. We want to make it improve. We need some improvements in that. Then, when it comes to radiation, there are two ways to handle the environment. One is that we protect human body and humans over there, or we try to protect the environment there. Otherwise, and otherwise means we try to protect our space shuttles from radiation. Then, when we protect it, there I have, as a physicist, I have some questions that when we use certain materials, those materials should also have some lifetime. So, if they are exposed to certain radiation for a long time, will they be equally shielding everything or not? And things like that. So, there are so many questions. A very, very important thing, which is totally not ignorable and very well known, is the difference of gravity. Gravity is changed, I think, 6, 7 times lower. I will show you the numbers later on moon, and it is gravity is also way smaller on than Earth on this Mars. Now the problem here is that if due to gravity, we all know that human body has problems, and that is something very well known, and people are working on it, which is totally understandable. But there is another thing which is kind of bothering me also, that is it possible because all the chemical processes which are taking place are in the on the Earth's gravity. When we go out in space and gravity changes, will the chemistry remain same? Because we don't talk about it, but chemistry plays a role there. Talk about carbon, oxygen, nitrogen, whatever it is, it has certain field, gravitational force. Due to Earth, it is due to Earth's gravity, it is balancing its weight. So when we go outside in space, things will change also, but we don't know how to handle it. Oh my God, this is again okay. Anyway, please excuse my typos. I did it very quickly. So we have to learn how to handle the difference of gravity. Then we have to keep the environment of the spacecrafts good. There is another thing, I have been attending some presentations, that this is totally understandable, that the metal in the space shuttles, it can go through corroding, and due to that corrosion, it is possible that bacteria is created, and that bacteria is a different type of bacteria. And I don't know if the in the presence of at least I think that this is worth studying, that in the presence of that environment, how the bacterial behavior will change. It may not be the same bacteria which we have on Earth. And bacteria is in a way more important, because its doubling time is like 2 hours or so. So in 10 hours, for example, it passes 5 generations. So whatever happens to it, it can mutate very easily. And that's the reason that it has sometimes very interesting behavior. It has been known that sometimes people found bacteria protected, which is basically, typically speaking, it is aerobic bacteria. It needs air to breathe, but if it is stuck within the wood, it might survive. Sometimes they find bacteria surviving in the flames, in the volcanoes. So life is very unpredictable. Sometimes life can survive or adopt very unusual environments also. And bacteria is famous for that. All I know a little bit more about bacteria, so I'm giving example. But there are other lives also, forms of life which can survive. So we are looking for those more than human. Human is pretty. We think we are very strong, but we are not as strong as small creatures could be. Okay, so when it comes to changing uh, the gravity, as I mentioned, this gives the idea that gravity is, this is on Earth, this is on Moon. Moon is, I think, 1/7, something 1/6 probably, and this is around one less than 1/3, a little more than 1/3 of the gravity of Earth. Now, this is something very interesting here and very different. Temperature on Earth is, they call it 15 Celsius, but we know temperature of the Earth. It depends on where it is. On Moon, temperature variation is, which is discussed in this group a lot of times, around 200, more than 200 Celsius, 250 Celsius or so, during day and night, which is too big. And similarly on Mars, just because of the absence of the atmosphere, this can happen. And here it is also because atmosphere is very thin. Now, if we look at the atmosphere, we need oxygen to live, to breathe, for life. Nitrogen is very common. There are other gases also. But on Moon, this is the composition of gas. And when it comes to Mars, it is thinner, but very thin atmosphere. I know there are people here who are more expert in that, more knowledgeable. But this is something that it has some carbon dioxide, and it's not so good for life. We call it, we just need oxygen to survive, but free oxygen is not easily available. So the atmosphere on Moon, Mars, and even on Europa and Titan and those things, we don't know what is at least I don't know exactly that what are we expecting, but for Mars and Moon, we have some more information. So this is what we have, and right now we don't know if we can really create the habitable place for human beings or not. I mean, we are trying to find ways, but still it is studies going on. So now I come to radiation, because in the beginning I talked about radiation. So in the radiation, when we look at that, this is just like wave, and it is very easy to understand. It is just like I can pick up anything and start moving, and this is the wave, nothing different. Electromagnetic signals, which we call wave, is different because of the reason that they are like they are coming down and they don't interact with anything else. So that is the only difference, but they are like radio waves, radio signals. They are of the size of a few meters, and they are produced by radio antennas and things like that. Then microwaves are actually this is the size of wavelength. This is how big a wave will be, kind of. So this is something which is the size of humans. Microwave could be anywhere from here to here. Then it comes to infrared, which is basically needle's size. This is it goes to microscopic level later on. Visible light is very small, and if you have some idea about bacteria, it is even a little bit. Visible light is almost the size of bacteria, comparable to that. Then UV light comes. Okay, this visible light is required for survival. Infrared is okay. Radio signals we think are safe, but there are some studies. Radio signals are still okay, but microwaves are, there is some study, and I don't know to what extent it is there, but there are in certain cases if its intensity increases, because in radiation dosage is very important. But I'm not getting into that. But this is something that microwave is almost safe, almost, but we have to be careful. Similarly, infrared with the regular intensity, because we use infrared in remote controls and those type of things, which is almost safe. Visible light is required. We need it. UV light is bad because after the visible light, UV, X-ray, gamma rays, they are they are what we categorize as ionizing radiation. So ionizing radiations may damage atoms and molecules, and also may affect the cells, which body has a natural mechanism which is called autocorrection, but some of the processes, that's why dosage is important, autocorrection may not work in that case. Now these waves are not producing too much energy, but when it comes to wavelength, small wavelength, it is more energy and it can heat up the system badly. So that is why when we go for the X-ray for medical purposes, X-rays are could be very damaging. So for that purpose, we just expose that portion of the body to X-ray, which is really, really needed. Similarly, gamma rays are there. One thing which we don't mention here, these are only electromagnetic radiation. When we go to space, you must have heard about solar mass ejection, coronal mass ejection, sorry, or uh, solar activity and other radiation. Radiation is not limited to electromagnetic radiation only. Particles are created in the form of radiations also. There could be protons, electrons, and other particles which are produced in the form of radiation. In the Earth's atmosphere, we have those type of radiations. Too long. How long I have time? Okay. I think I will be done in that time. Okay. So there are radiation has again a big I mean, a lot of other things are needed or should be mentioned there. And that is another concern that, for example, ISS, another system, if there is a space mission and humans are observing that or taking doing experiments there, that area is not only radiation, which is we are talking gamma ray, X-ray, UV, and others. It is also the radiation in terms of an ionosphere. We have all the other particles and other things. I cannot get into all the details. So that is something which again we can protect a lot of it. Human beings can be protected a lot of those radiations, but still some exposure may be possible, especially during the repair or something like that. So all those things have to be taken into account or discussed in detail. This is something which is basically the same electromagnetic spectrum. This is a little bit detailed, more like technical language. And since this is something which looks like totally out of place, but it is not in the sense, because all the information about space we get from HR diagram, which I think everybody knows, that just measuring the luminosity and the surface temperature of star, we can categorize it. Now, when we go to extraterrestrial life study outside the, actually, I think that slide is somewhere gone. Anyway, that is something which is totally not discussed here, but that is another way to look at it. That based on this thing, we are looking at planets as stars outside the solar system, and this is the category. Now, these stars, just based on luminosity and temperature, we understand or we study what it is. Now, based on these uh, type of stars, we are expecting different type of radiations coming out of stars. Those radiations are only in the close range. Good thing about radiation is that high energy radiations don't travel too far, so we have a lot of empty space available. But these things are very important to study, because those temperatures, if you it is a very small picture, but if we have temperatures and not luminosity temperatures, at these temperatures we are talking about stars where the existence of life is very difficult. For example, in neutron star we are talking about, anyway, let's not go to neutron star, that is a little too much. Inside the sun, the temperature of the core or inside inner area can go to millions of Kelvin. So when we go to neutron star, it is thousands of millions or even more than that. So we cannot think about survival of life. So, however, the exoplanets, we don't know if the exoplanets may have that type of situation or not. Now there is a very interesting equation, we call it Drake equation, which says if one planet, to me it's a joke, one planet in the solar system has a probability of life which is 1 over, it used to be 1/9, now it is 1/8 because there are 8 planets. Then we look at other things, and in that way, I had a number here somewhere. It is last year, I think I missed it. That is something that is 10 raised to power 1 over 10 raised to power at least 38 digits, which you can write to get to that. So let me see if I can find that number somewhere. Yeah. Yeah, this is the number. 2685,000, 10 raised to power 2685,000 times. That is something that if there are so many things there, I don't even know how to call it. So one in that is the probability. So probabilistic calculations, statistical analysis, they are not really something useful. But the only way to find or to look for life is like in even in asteroids, we try to get samples to find if they are amino acid. When meteorites hit Earth, we see that the rocks have some signatures of life. That is something which makes sense, that organic molecules are there, so there is a possibility that at least organic presence of organic molecules indicate that they may come up together to create life, which we have here also. Sorry, somehow I missed this part. So this is basically that how we use radiation to study, and I just mentioned it for completeness that outside the solar system, it's more like we can think about it, but we don't even know that if there is a in the near future we can really find any signatures of life. So however, based on the radiation biophysics actually is basically the how the radiation interacts with matter, and if we know that, then based on that we can see how the radiation will interact with the biological systems, with organic molecules and things like that. And that is something which is basically a big part of radiation biology, and that is very relevant not only on Earth. It is a very important topic of study on Earth, but at the same time, it is equally important for the space biology. I am not going to discuss this. Sorry. There are a few ongoing projects, and there are so many things which are going through it under this category, that extensive study of planets and satellites to find out the possibility of life or signatures of life. Then we try to create safe environment for a relatively longer term stay of even astronauts on moon, even if not Mars yet. Plus, we are trying to look for that if plants and other things can be some vegetation is possible over there, we can grow it manually. Then how to make long term travel in space possible for human beings, plus long term stay for the experimental study on ISS can be made a little bit more comfortable. And also, if there is some work which can be done, that the biomechanical effects can be controlled in space to some extent. And I think this is what I will stop here.
Yeah,
Okay.
question for you. So your book, is it available in the U.S. Clear Lake Library?
My book?
Your book.
Okay, my book is published. Electronic copy is available on even Amazon. But right now, the hard copy is still not there.
Okay, so the 2014 book is just like,
Oh, so 2014 is available in the library.
so for this library here. Okay, good.
But that is very technical. 2014 book was very technical because it was based on a quantum statistical physics with this many body theory, which is very mathematical.
Okay.
Even I don't know what I wrote. I'm sorry, I'm just kidding.
But the 2025 is available.
This is more for students who are, it's not a textbook, but it is more for students who are preparing for higher education in physics.
Okay, that is available electronically.
Yeah,
Okay,
that is something which is not yet available, but it will be soon.
will be. Okay.
Yeah. It is published officially, but university doesn't have it.
Okay.
Okay.
I got a really hard question for you. First of all, good overview. I enjoyed it. The search for life out in the universe, right? It has a presupposition that it started somewhere, right? And so, what is your interpretation or understanding of how life started?
Okay. I'm sorry, I know that this is a little tricky question, but I'm just giving the scientific point of view. Actually, There is usually what people talk about it. I have just taken a couple of courses as an undergrad student in biology, and there was one of them they call it accidental existence of life. And what was that? I'm not getting into Darwin theory or anything else. That is something different.
Right.
This is like that. That is one of the scientist's point of view. That life actually, what happened was that there were some amino acids, organic molecules available, and when they are in the fluids like water, then they accidentally they come close to each other, totally accidentally. It is something similar to that a monkey can type words for sonnet.
Right out Shakespeare.
So that is something that is, I'm giving you weird example, but it is more like that within the water, with the water, when it was flowing in the fluid, then they come close enough to each other and accidentally a DNA was formed. Actually, it doesn't need to be DNA. Even RNA, which is single chain, if it is found, it can develop the ability to reproduce and create duplicate molecule. And that is the start of life, that it can automatically grow.
Okay. So that's, you're talking about like abiogenesis, right? That's what, or chemical evolution or something like that?
No, that is nature. It is just the creation of first molecule.
Okay.
I remember there used to be a theory in like biology courses I have studied that amoeba is considered to be that's why I especially mentioned that amoeba was considered to be the first animal created, first
Yeah.
living organism. Not animal.
So like on Earth, right, the earliest signs of life, chemical life, was about 3.8 billion years ago. And
Yeah,
so
no.
Earth was had very hostile conditions then. And it's
Yeah, in
hard to
actually, this is something where there are certain things like, if you look at this, always people talk about life in oceans or in water.
Yeah.
That is the first form. And that is small life like bacteria. There are, I think they are called tripods. They have some small creatures, tripods with the eyes. So I don't have anything else to say.
Okay.
So they consider that is the oldest animal, which they can call animal. But this is something that where there are like, because we don't have so much information about that, so there is some supposition and some.
Oh, yeah, it's a challenge. I know there's not an easy answer. I just was curious.
No, it is more opinion based. It is still not
Yeah.
any scientific answer.
Okay. Good answer. Thank you.
Any other questions? Yeah, could I amplify on that a little bit? If we have these ideas of what conditions we think are required for life to develop, and you're looking at exoplanets with the tools we have, which are things like observing spectra, with tools like the James Webb, what should we be looking for in exoplanets to give us an idea of whether life might have a possibility there?
Okay. One thing I think is, exoplanets, of course, we have so many things to look around for that. But first of all, I'm not even sure that exoplanets are the planet for which I can understand that what is the atmosphere there. Because atmosphere plays a crucial role there. And the other thing which bothers me a lot, very big question. Should we expect the same chemistry outside Earth which we have here? Because gravity plays such a big role. And what do you think, Brent?
About what signatures or, well, I mean, James Webb's looking a lot at, like you said, atmospheric signatures. So they're looking for things like oxygen and carbon, things like that.
No,
It's an open topic, so.
Sometimes I think it is possible that I'm just now talking about some fiction, science fiction, that if carbon is creating a chain here, it is quite possible when the gravity is reduced on moon, for example, then carbon doesn't make a chain. Instead of carbon, silicon makes a chain. Because the heavier element becomes a little bit less heavy. So you don't know. Then they start talking about it. If it is silicon-based life, there was an idea, then the life cannot grow that high. It cannot grow high on Earth because of gravity, but it can grow high on Moon, for example, or maybe somewhere else. So there are so many things that exoplanets are still far away. I guess. I'm sorry.
Well,
This is
you
how I
have an
feel.
opportunity.
It's still too far away.
Any more questions? All right.
All righty. Rick, did you bring some giveaway magazines tonight? Guess Rick's not going to pay attention to us. All right, so I'm assuming Rick's got giveaway magazines up there, even though he's not paying attention. All right, another thing I want to tell you guys, we're going to have tonight, in addition to our door prize, we're going to have possibly 3 special giveaways. So we're going to give away a telescope, and that was this long story. Anyway, but then 2 sets of books that were donated by David. These are famous and outstanding books. The Night Sky Observer's Guide. These are high dollar, cool books. I don't know why David doesn't want them, but it's very nice of David to donate them. So I'm not going to give these away as door prize. I think we'll do a special drawing. What we'll do, not a special drawing, I'm going to pick a number, and you guys, whoever's interested in, like there's 3 or 4 people who want these, we'll see who gets the closest number or something. But I don't want to just give these away. I only would give them to people who actually want them. Okay, so that's what we're going to do. So during the break, you guys can come down here, look at this telescope, look at these books, and see if you're interested in them. The other ones are Annals of the Deep Sky, some Dennis Webb books here. So we'll give these away as a special giveaway tonight. All righty. So after the meeting, we'll get together at Mod Pizza. Mod Pizza's it's up at Clear Lake City Boulevard and El Dorado Boulevard. Get together there and talk about astronomy and other things. Everyone's welcome to attend. And we will take a 10-minute break and get back together with the second half of our meeting. Gonna get that beautiful thing?
Oh, I love it.
Well, okay, you can be one of the bidders on it.
Yeah, because tomorrow night I'll bring the big binoculars,
Cool.
the new pair that I got.
Looking forward to it.
Yeah.
I wanted to mention to you that we're going to have a start party at Edwin Mender Library. It's a week from tomorrow. Tomorrow night's the one at the you're welcome to come
At the golf course, right?
But the
We
one,
actually live very close.
yeah, well, you can go to that one too. So it's at Magnolia Creek Golf Course tomorrow. You guys are welcome to come to that. And we also got one week from that. Edwin Mender Library in Cedar. And that one, there's usually a lot of families with kids and people there. So if you want to come to that, you know, I was told by some people they probably had to tell us what has to be done. Everyone's welcome to
So that'll be on the 22nd.
So tomorrow night, 15, at this golf course, and then on 22nd at Edwin Mender Library, you're welcome to come. I just want to make sure you didn't. I had someone tell me that
they probably couldn't come and say, anyway, I want to let you know about
Thank you.
that. Okay. Oh, yes. All right, come on, you need a telescope.
Wow, wow.
I've got this telescope, I've got these cool books here.
Can I take a photo first?
Yes, do you have, did you get a door prize ticket?
What is called door prize?
Did you get a door prize ticket?
What's the
Okay, when you came in, you didn't get a door prize ticket?
Oh,
The little ticket? Yeah, that's, okay, so we're gonna give these, okay, so we're gonna give these away. No, you're not paying. This, everything here is free. We don't do money. But you can, if you're interested in the telescope, you can have it on this one. And we'll do a drawing.
how do you use it? Can you teach me?
I can, but I don't want to.
That's
But
fine.
it's got a quarter 20, you put it on a tripod, and you can look through it, and look at things like the moon and stuff like that. You know what you should do? Okay, we have star parties. We're gonna talk about later. Like tomorrow night we have one, I know you keep golf course. Okay. Do you live around here somewhere?
No, I live in a city.
You live at where?
Kind of inside of city.
What is that? Oh, okay, so tomorrow night we start party in Magnolia Creek Golf Course. But then, if you second, we're gonna look at what library. So if you want to come and look through the house, we're gonna
I
do it.
joined the one in Rice. So there's one night that offers access to their building and use
Yeah, no, that's cool.
it.
Right.
So this is like similar but smaller size.
Yes, but you can have this one if you want. If you want it, nobody else wants it. But we'll have a kind of a drawing. But also, but you want to go to a star party, so it's kind of fun. We set some stage out on the parking lot and stuff, and okay, so you know our webpage, right?
I can search. You can read the.
Well, I gave you that. That's how to get on the email distribution. Here. How did you find out about us? Who?
Join the
Meetup. Okay, hold on.
Science. So they asked me group. So I joined that and somebody posted this event.
Okay, so I know I got one of my copies. Okay, on our webpage. That's our astronomy club webpage. All right, so there's a calendar on this webpage.
Wonderful.
And this calendar, on the calendar, it shows you all of our different events. You're welcome to come to all, any of them, all of them. That's my astronomy club.
Okay, thank you.
That's what I post all my pictures. What's your name?
Paige. Paige. P-A-J-I-A. It's a Chinese. Yeah, J is
All right, good. Well, video, how are you?
Very good. How do we sign up for?
You got what?
Do we sign up for?
I'm gonna tell people to pick a number. Between 0 and 1. If you don't know there's an infinite number of numbers from 0 to 1, you shouldn't have a telescope anyway. Sorry. It's the way I see life. I'm
Between 0 and 1.
You know what? If you don't know that, you shouldn't be here. Sorry. Sometimes I just gotta say it.
Yeah.
No, the books are great. I don't know if you looked at them. These are like famous seven. The nice guy, observer guy. These are outstanding books. I don't know who's way out there. Anyway, I don't know. They're really good if you want them. We'll give these away. If you're the only one that wants them, they're yours. Perfect. That's good. Okay, I think 10 minutes is up, and we're going to get started. I hope I'm right about that.
We're gonna get started. Someday we're gonna get started. Well, yes, we're gonna get started. Would it be okay with you guys if we get started? All right, thank you. Okay, so I have a DIY astronomy tonight. Let's see if my pointer's working. Human bodies, they radiate. So I thought this would go along with Dr. Masood was talking about astrobiology and everything. So last month at our meeting, David, during Star Party News, showed pictures of Astronomy Day. And included in those pictures of Astronomy Day, he showed pictures of our radio astronomy setup. And included in our radio astronomy setup, we had a live demonstration of a radio telescope. Okay? And the way this worked is this radio telescope, when it is pointing at the cold sky, our waterfall graph over here would indicate blue, see? But then we would tell people to climb up on the step stool of science, take your 2 steps up there on the step stool of science, put your body out there, and then our waterfall graph would change colors to indicate the radiation off their human bodies. Now, this is a really fun display. We had a blast doing this. But later at Mod Pizza, somebody said, or a group of people said, what exactly were we measuring during this demonstration of our radio telescope? And so I expounded and I said, I assume it's a combination of the electrical activity in your body and your body's quasi black body radiation, or the heat in your body. But other knowledgeable JSCAS members, namely Jerry over here, said he thought that the electrical activity in your body probably wasn't strong enough for us to detect it with our radio telescope. And he says that since we're operating at 12.7 gigahertz, we're probably way too far down the curve here on the black body radiation to detect anything. And he's right about that, because so you look at this curve and it cuts off at 100 micrometers. Our wavelength is like at 23,000 micrometers. So we were like way off the chart, right? So Jerry's making a good point. Now, since B and Jerry are like super doctors because they teach other doctors, they're like super doctors. So I'm going to assume that they know what they're talking about. It's probably not the electrical activity within your body. I probably just made that up somehow, thinking that maybe that's what it was. But I was thinking, I wonder if there could still be enough signal from our quasi black body radiation to detect it with our radio telescope. So what we're going to do is we're going to explore this idea and see if that's possible. So we're going to do some analysis. We're going to look and see what's the level of this signal coming from our human body, from our heat, and compare that to how sensitive we think our radio telescope is, and see if there's any chance we actually might be able to detect this. In order to do that, we're going to use a little bit of math. And I said it before, and I said it again. Math is fun. I'm sure you will all agree. Yes. So question number 1, what is the temperature of a human body? So if you've ever had a fever, it's like 98.6, right? 98.6. But we're going to need that in Kelvin. And Kelvin is a scale that's referenced to 0 degrees or absolute zero, which is the temperature where particles are nearly motionless. 0 degrees Kelvin is absolute zero. We put our 98.6 degrees Fahrenheit in our Kelvin equation, and we get something that's just about 310 degrees Kelvin for a human body. Question number 2, how much signal can we expect from a 310 degree Kelvin human? So what we do is we take our 310 degrees, we put this in Planck's radiation law, which is the law that describes this curve, these black body radiation curves, plug it into some kind of plotting program like MATLAB or other, and we get this nice black body radiation curve, okay, for 310 Kelvin. Then we look at our frequency, which is 12.7 megahertz, and we find out that the brightness of our black body radiation from a human body is this number here. Now, take note that the peak down to our level is like over 363,000 times higher. This is a log scale to make it fit on the scale. in case you're trying to figure out why it looks like that. It's a log scale. But the peak to where our signal is 363,000 times more than that, bigger. So it is a tiny little signal, just like somebody observed. So question number 3, is our black body curve even close to being correct? So what we'll do is we'll pull out a book like the Radio Astronomy book by John Krauss, and we'll look at their curves and we'll compare them to our curves. And we say, okay, we look at them and they're just about the same. So we think our number's probably about right. So we're okay on that. Question number 4, what signals have we been able to detect previously with our radio telescope? So we first want to see how big is our signal. We want to figure out how sensitive is our radio telescope. Is there any possibility we actually detected this signal? So with our 2.1 meter radio telescope, in the past, we've been able to detect the Crab Nebula and Cassiopeia A, which are both supernova remnants. We've also been able to detect Cygnus A, which is an active galaxy, excuse me, and Cygnus X, which is a star-forming region. But what you see about all these is they're all on the order of about 1,000 Jansky. Jansky's being the unit of flux density, which is used in radio astronomy. So they're on the order of about 1,000. We've been able to detect something about at that level. Question number 5, how does our human body signal compare to those previous things we've been able to detect? So our black body radiation was brightness, and our previous detections were flux density. So to convert between those two, we just take brightness times our antenna beam size, and we can get flux density. So it turns out the flux density is actually 51 million, over 51 million, which is way bigger than 1,000 Janskys, right? 51 million compared to 1,000 Janskys. So that's just a pretty good idea that we can probably detect this with our radio telescope. One more thing. So some time ago, actually it was in April, I showed a presentation about how to measure the temperature of the moon with a satellite TV dish antenna. You guys may remember that. Okay. Now, when we did that, one of the things we did during that experiment is we pointed our radio telescope at the wall of a garage, and then we pointed up at the cold sky to derive a parameter called system temperature. And here's that slide from that magical moment when I showed this all to you. All right, here's the garage, here's the cold sky. And when we did that, we got like a 3.2 decibel difference between these two. So if the wall of the garage is 82 degrees Fahrenheit and a human body is 98.6 degrees Fahrenheit, if we can get a 3 dB signal off a garage, we can get a way bigger signal off a human body. So that too makes us feel like, yeah, we're probably able to measure the heat from a human body. So in conclusion, I think it's probably reasonable that a human body signal at 310 degrees Kelvin can be measured with a satellite TV dish antenna radio telescope at 12.7 gigahertz. So I think it's probably reasonable that we're doing that. So I think we probably are measuring quasi black body radiation from a human body. Not the electrical signal thing, but the heat. And I also want to point out that this is actually a really fun radio telescope demonstration for public star parties, because it kind of demonstrates how we can measure thermal celestial objects. We're measuring thermal from a person's body, but a radio telescope also measures thermal celestial objects in space. And it's a lot of fun. People love doing it. So this is a great thing we can do at public star parties. So this presentation and all my other adventures in astronomy are located on my webpage. Any questions?
So Doug, how did you figure out this would work as a demonstration at the event?
Because I saw somebody else do it first. I got to tell the truth. I mean, I saw it on the Sarah webpage. I mean, I would like to tell you that I think of all these things myself, but I don't know. One of these days I'll think of something myself. Anybody else?
So it's when you're looking at the background radiation,
Yes.
and then you interfere with your body, are you measuring your body or you're blocking something else?
Are you talking about when I'm looking at a cold sky or when I'm looking at a human body?
When you're going from the cold sky to the human body.
What's your question?
So are you blocking any radiation?
Yes.
Or
Yeah, because, okay, a video, the field of view, the beam width on this thing is 3.75 degrees, tiny. So if you get a big fat human stand right in front of the thing, they're way bigger than 3 degrees. Yeah, so they're filling up the entire beam of the telescope. Yeah.
I can attest to that.
Yeah. So what I did is I had them climb up on a step stool, and they stood right in front of it. And if it wasn't working, I told them to hold their hands up and some other stuff. And it was fun because we had little kids would get up there. I'd say I want a small volunteer and a big volunteer. And a little kid would get up there and they just get a little blip, like just barely turn green or something from blue to green. And then their parents would get there and turn, bright red. So it was fun. We were talking about who's got the hottest mom, and stuff and all. It was a blast. I mean, we had a blast doing this.
I think he's got a good question though. Are you actually measuring the temperature of the body of the person?
Yes.
Or the fact that prior to the person stepping in front of it, you're measuring the background sky that someone steps in? Are you just seeing a change from the cooler temperature?
Yeah, you're seeing the difference between the cold sky and the hot body.
Right, but you're not measuring the temperature of the body.
We're measuring the radiation off the body. I mean, we don't get 98.6.
I don't know unless you try to calculate it. I guess I think I understand.
What are you asking? Stop eating and talk.
Or are we
Yeah.
reading something from it?
So if you have your antenna and it's measuring the background,
Yeah,
like the sky, I don't know what temperature that is.
2.7 Kelvin.
Okay, 2.7, and then a warm body gets in front of it.
Yeah.
All of a sudden, the signal goes from 2.7 to whatever.
Right.
80, 98, 310.
Yeah.
You're seeing are you just seeing the signal change from that, or are you actually, I guess you didn't show a calculation like where you try to calculate the temperature.
No, we're not calculating temperature. We're
You
calculating.
calculated the temperature of the moon, right? When you did
I did that,
Tried
but
to do that same
yeah,
thing.
this is different. No, all we're doing is we're measuring the difference between 2.7 Kelvin and 310 Kelvin. That's what you're doing. Because when you look at the cold sky, it fills the beam with the cold sky, and you put a person's body in there, it fills the beam with their body.
So it means
You're measuring the delta.
Yeah.
You're measuring the difference between the two.
difference of temperature.
What?
That's what I was saying, it is the difference of temperature.
Right. It's the difference between the two.
But one comment I want to give, I hope you won't mind. Why you are calling it quasi black body? It is just a black body.
Well, okay. No, I said quasi black body. Quasi black body because I want to be able to use the Planck radiation law. I want to figure out some way to calculate it.
No, but I mean, black body is something which you can use anywhere. I'm sorry.
Yeah, she's
black
asking
body-
she's asking why not just call it a black body? What's the quasi?
Yeah.
Because you're a person that's not a black body radiator.
Black body radiation can be applied anywhere. I mean, it is totally hypothetical.
No. Your body is not a black body radiator. It is not. Your body is. This is a quasi black body radiator. Your body is not a perfect.
No, I really enjoy that word quasi.
No, but the reason I'm saying that because your body is not a perfect absorber or a perfect radiator of radiation, so it's not a black body.
Even stars are not, but those are all black.
Well, they're not, but your body, human body, is nowhere close to being a real black body. Any other questions? Any reasonable questions?
So when you measure the moon temperature,
Yeah.
I don't remember, I forgot about it. So what was the temperature itself that you measure with your red telescope?
What are you asking? What the temperature was?
Yeah.
210 Kelvin.
210 Kelvin, which is less than the 300,
What?
which is less than the 300 and
Yeah.
50 Kelvin or whatever.
Right,
on the
right.
body.
That's
So
right.
that's for a full moon or a new moon?
It changed. Were you at my presentation? It changes with the phase of the moon. So it depends on where you are in the phase of the moon and what the temperature of the moon is. It does change. But if you want to see it, it's posted on my webpage. I actually posted just how to measure the temperature of the moon with a satellite TV dish antenna. And you can go through, I went through every step on how to do it and all the calculations if you want to see it. And I compared to actually two other sources and we actually got the right numbers with it, which is pretty amazing because I mean, it's a satellite TV dish antenna, right? So, okay. Any other questions? All right. Thank you. We're going to move on. Al, what's up in the sky? Woo-hoo!
Good evening. I went to the dermatologist. Yeah, I thought I hadn't changed the October to November, so you caught me. We have a bunch of meteor showers in November. This didn't get changed either. The toroids and linoids. And I guess the linoids are most famous, I think, of all the meteor showers. Is that right? Yeah, it always happens in the fall. And I left in here the rhinids, because I saw a really good one, which I put in a slide at the end of the presentation. But I read later that it's noteworthy because it's one of the meteor showers that produces the most amount of fireballs. So maybe next year we should put a little bit more effort into looking at this particular shower in October. So I did this for a binocular object, which is Saturn, because Saturn's really cool in the binoculars, but then it made me think of something else. You can see this is a stellarium view, mainly so you can see the moons. And then here I have two different views of Saturn with the moons. One is to show that they move quite a lot in one portion of the night or night to night. But I brought this up because I continue to try to find some way to measure the quality of the sky at night. And I'm not talking about how black it is necessarily, but maybe transparency or other type of properties. And one of the things I discovered looking at Saturn is some of the moons are like 12th magnitude, which is pretty reasonable for most average telescopes in the middle. And then as you get to a bigger telescope, which I have, there's some 17th and 18th magnitude. So I haven't gotten a chance to yet try this, but maybe I'm putting it out there for people to start looking at this and seeing if they can see the quality of the sky based on how well the moons of Saturn show up for you. But since you can see they move around quite a bit, you're going to actually have to pull up something like Stellarium and figure out who's who when you go to try to look at them. Because then you would be the only way to know which one is the one with the magnitude that's high and the one that's low. Okay, another binocular object is M15 globular cluster. So my research says that one of the most interesting aspects of this recently is they have figured out that there's an intermediary IMBH, intermediary mass black hole in the center. And the way they were deducing that is they found this rogue star who's kind of either moving through or being ejected from the globular cluster. And the only way that it could be moving that fast is if a black hole slung it out. So I don't know. It's very interesting when you dive into some of these objects instead of just going, oh, that's kind of cute. That's kind of neat for the night. And you try to start like figuring out some information about it. There's also, which I think this is piece one. This object down here, it's a planetary nebula. And you can see it right off of the, looks like a handle, doesn't it? But what they're doing is they're showing you how to like find piece one by tracking or by star hopping through the globular. And I'm not sure, I don't think that's very bright. So it would be a photography element. You would have to photograph this in order to have that come up because I think its magnitude is worse than like 17 or something. But once again, something interesting to try. Think about, when you're doing some observing, maybe I could see that. So the first telescope object is the Great Barred Galaxy in Eridanus. Is that right? Yep. This constellation I really like. There's a bunch of very interesting stuff in it. And the left object, the left view is sort of what you would typically see in a telescope. And then the right view obviously is like a Hubble image or something like that. But it's also considered a double barred galaxy. Let's see. You can kind of see that there's this bar here, but there's almost a bar like here. And so that's where they get this from. But it's really elongated, so it's really, really cool. So the next object or group of objects is 1399. And it's really the Fornax galaxy cluster, but I often need to find for like finding it in a telescope computer, like at least one NGC number, something like that, that I can key off of. And this group is really cool. I think I was looking at this during this fall, and I like to try to highlight things that I've either seen or I've been looking at recently, because like in the fall, there's less galaxies. And so I'm really hunting to try to find 2 or 3 galaxies in a cluster versus just single galaxies. And so this is one that I pretty much think that I was looking at this season. But it's just so cool. You got some ellipticals in there, a couple of edge-ons, like some edge-ons right here, and then here. And then, of course, I think this is the one this is the 1399, this spiral. Next object is NGC 467 and 470, 474. And this is part of an ARP group, 227. And what I thought was really neat is on the left is what you typically would see. And then what do you see on the right? I mean, that's like a completely different image than we observe, right? So this right side picture is probably a Hubble or a Webb telescope view. And I really like these shells down here. This is just really spectacular. And it's like, oh man, I wish I could see that in my telescope. I keep thinking about the telescopes that use adaptive optics. And before, I thought adaptive optics was they had a primary mirror with a bunch of movable mirrors, and they were doing like this. And then it never really occurred to me that that would be insane, because that would be very hard to do. And what they actually do is they beam the light off axis to a separate set of 2 mirrors. One of them is a movable mirror that has segments to it, or some other type of a mirror surface. And then the other one is actually looking at so they split it. And the other one is actually looking at the image, trying to determine how to modify it or adjust it to make it adapted. And adaptive optics is trying to match the turbulence of the air and the seeing quality and trying to blend that out, if you will. And I don't know, I guess it's possible an amateur scope could eventually have something like that. Probably this little thing I'm talking about here that fixes the image is probably going to be worth several telescopes. But hey, ZWO can do a lot of things, right? So NGC 520, this is really cool too. This is an interacting galaxy, but what's cool is it's got a very low magnitude, only 11.42. I can't remember if I've looked at this recently or not. This is on the left, more of a typical view you'd see. And then obviously this is a very cool image over on this side. The next one is NGC 835. And this one, I believe, yeah, this was my best objects that I looked at with my telescope during this past fall with ESP and Fort McCavitt. And that's why I put it in here. And it's just really cool. It's like a chain of objects. And you've got sort of the elliptical over here, and then edge on, and then a nice face on. And this is sort of a ring. They classify galaxies several different ways, and this is sort of like a ring galaxy, which is unusual. I started working on the Hickson group of galaxies, clusters, because I kind of did a lot of the ARPs, and I was starting to look for other lists that I could use. So that's where I came up with this. Yeah.
Can you go back up, just at the back? Is this one picture or 2 pictures?
This is one picture.
Okay.
I don't know if this was a wide field view using like a astrograph or something.
Okay.
It might have been a mosaic. You know, I go on the web and I try to find something representative of what I think is kind of typical seeing versus like the super glorious, you know, Hubbles and James Webbs.
So is this a Hickson galaxy group here?
Yeah, this is HCG 15.
15. Okay,
Yeah.
that's 15.
This is really cool. This is fun.
Do you remember what constellation this was in?
No.
Okay.
I didn't quite pick things all from one constellation like I usually do.
Okay.
So this is the last one of these slides. This is a Hickson 10, HCG 10. And on the left is very representative of what I was able to see. This sort of odd one here, and this one. I didn't see these little wisps here, elliptical in here, and then this little edge on. And then you go over to the super duper picture with the nice labels, and this is so cool looking, but oh well, someday. So what do we have next? Recent astronomy news. I only have 3. I have a couple of really good ones. So the very first one is James Webb. And I picked this one because I also like the idea that people are still figuring out things and inventing new things. James Webb is like a multi-billion-dollar telescope, but they had this problem. The top row is what the Hubble or the James Webb typically sees. But if you look at the bottom, these are adjusted pictures, and you would never guess that the real image is these ones on the bottom. So this is Io in the middle, so obviously the picture above it doesn't look right. Well, a team from Australia created a bunch of software that would do basically in the cameras, there's a bleed over problem. When you absorb for a certain length of time, adjacent pixels will get some of the light from the one that it should be. So the central one will have a certain amount of light, but once it gets to a certain level, it bleeds over into the adjacent pixels. And so it's a fundamental problem. And then there's the fundamental problem of you want to do as long of storage as you can because you get a higher signal to noise ratio. So you can't just do a lot of really quick pictures because then your camera doesn't really get its best capability. And so I thought this was just really cool so what are they going to do with this? I don't know. It's probably for fundamentally small and faint objects that they're going to start using this on. I don't know about processing old pictures or not. It's not a real-time capability. It's more of a post-processing effort. But that was very cool. And then this is number 2 out of 3. And then this is the first time astronomers have managed to capture a radio image showing 2 black holes orbiting each other. So the center object, I can't remember. I thought the center object was like a quasar or something like that. And then these 2 black holes, and this is a graphic of the arrangement they are. But you can see in the center image how they're able to separate it. And so that's just really cool. I'm just really fascinated with the radio astronomy. I have a calling. So my last one goes back to the Orinids. So I was Orinids. So I was talking on the ESP field, the small field where there's about 10 of us, and I was talking to a couple of people, and somebody was fidgeting with their equipment. So most of us had our heads down like this, and I don't know, I was probably doing something like this, and then there goes by the perfect meteor that you would always want to see, at least once when you're out there. And by the time that I was going to say something, it was gone. And I felt so horrible because it was so good. And when you're out on these fields, we see meteors all the time and people are going, ooh, and you're busy, you're busy if you're an observer, particularly, whether you're on the computer or in the telescope. And so this one flew by, and that's why I did it. Now, I didn't get an image of it. This is not my video, as you'll see. But I tried to find a representative one. Now, mine was not this long. But this is what you want to see. So mine was probably a third of this or something. And it seemed a lot closer. But I didn't get a video of it. I didn't have time. But 2 or 3 years ago, I was out on the ESP field at X-Bar Ranch. And it was just me. And this was a couple years after COVID. So a lot of people weren't doing very much. And I was observing over here. And a son and a father were using a telescope about 30 feet away from me. And then all of a sudden, it was like somebody drove onto the field with headlights or something. And I was going to turn around and get upset, because that's how I am. And I didn't say something right away, but because I saw this huge meteor coming across and it lit up the field. Now, it was burning a whitish color. So that didn't indicate a meteor. If anybody knows, most meteors are more on the orange side or yellow side. So instantly I knew it was probably something re-entering, from space. We didn't find out till the next morning. They caught part of it. I was trying to get my video going. It was pretty funny. But I did get a video of it I downloaded it the next day. Some little news program in Texas got a little video from somebody. And we found out it was a Chinese rocket re-entering after about a year orbiting. And so I thought that was like a once in a lifetime. It broke up and it was so cool and stuff. But anyway, and any other questions? I never asked for questions. I'm sorry. It always slipped my mind that people might have questions. Sorry.
So when the low light went over, did you hear anything?
No, I didn't hear anything.
Because, there are people.
And I didn't see smoke.
Yeah, sometimes people say they actually hear something in the atmosphere when they're really good. Yeah, and the second question is, okay, the Orion is, I was out the same place you were, and I was trying to doing long exposure pictures of Orion, trying to get any meteors, and I did it for 2 or 3 hours. I never saw even one, but I saw a whole bunch of meteors, but I didn't see them like they were emitting from Orion. Is it like they're so far from Orion that they're outside the field of view of Orion itself?
I think that if somebody was to really sit down and take the track, because they obviously know what's going on, because they hypothetically believe they know where the comet came through, I think it has to do with whether we're getting glancing blows or not, because our orbit's not perfect all the time. I mean, we know this from space travel that, our math is not perfect. And so I think there's a lot of give and take. And I think also, I don't think it's a perfect principle that they're all like going or we're all hitting it like this. I think the stuff is still like this. I don't think it's stagnant. When it came off the comet, I don't think it was stagnant. So I think there's some issue with some velocity already going before we hit it.
I don't know. I didn't get any.
Thank
Any
you.
other questions for Al?
Any other questions?
Oh, there's a question up there, Al.
Go ahead.
You have two small errors on the first slide and the last slide. Because the meteor showers are named after the constellation. So you have Illinois, it should be Leonid.
Oh, Lenoids?
LEO.
Lenoids.
Constellation on Leo, so Leonid.
Right.
And the last
Orionids from Orion.
Orionid, not
Right.
Orinoid.
Orion, right.
Wrong spell.
Okay. Any other
Go to
comments
the
or
first
questions?
slide.
Other than wrong spelling?
Actually,
Thanks, Al. David,
To your comment, Doug, Connie and I were at one time at the fort, and we heard one.
oh,
It was traveling east to west. We're working on the table. We're setting up the scope, and had that oh hecky darn moment because we didn't know what the SAM it was. Looked up, it was orange and making a very loud screech as it came across the sky. But there was no boom or anything. It didn't hit, obviously. But
what did it sound like?
a high pitched screech.
High pitched.
Yeah.
I heard when it's like sizzle, kind of like a sizzle.
Yeah, there was a kind of a sizzle, and it initially just scared the crap out of us when we first heard it. Then we looked up and saw it just streaking across. And it's like then our hearts stopped, and we got back to what we were doing. All right, Star Party news. Well, it's right. Enter, right? Yeah. All right, we had a little bit of busy work here. October's trip to Fort McCabbett.
Hold on, Dave. Hey, guys, will you please not talk during the presentations? Will you guys please not talk during our presenters? You two, hold on. You two, hold on. No talking during the presenter.
Club's trip to Fort McCabbett, then it was El Dorado, and then Armand Bayou, which didn't happen. Neither did the Sun and Moon Night at the George. I'll talk about that a little bit. And then on November 4th, there was the UH astronomy and physics students one. Came out pretty good. Our last two events so far for the year is tomorrow, Saturday at Magnolia Creek, and then November 22nd at Evelyn Meadow. This is a rebook from earlier. Sliding into 2026, we've got the trip to the fort on March 19th to the 23rd. This got morphed into the multi-club Messier Marathon. That still has some activity going on. We've got 14 clubs potentially interested in
We had a Zoom a little while ago, and I told them you really just need to chill out until we get within about a month to 6 weeks ahead, then start seeing if there's interest. This real sweet gal from the San Antonio Club is wanting everybody to sign up like right now. I said, it's not going to happen. April 9th through the 12th, we've got our own, courtesy of the Fort, allowed us to have our own dates, since the March dates kind of got hijacked, if you will. Doug kindly informed me 5 through 10 is 2026 is the El Dorado Star Party dates, and then 8th through 12th is the club's trip to Fort McCavitt. Hot off the press at the break on my phone. Joe Califf of HAS would like to come maybe to the December meeting. I don't know what's on the December meeting, if it's going to be a DIY type meeting, and talk about the new revamped Texas Star Party. For those of you who don't know, there have been some problems over the last couple of years. And how do I put this nicely? Let's say with a coup or a resignation, effective about 2 weeks ago, Texas Star Party is under complete reorganization from the top down. Mike Faraz, past president of HAS, is now the immediate president of Texas Star Party, and he's got Will Young and Joe Califf helping him out. And they're talking about reduced rates, better flexibility, with staying different days, 3, 5, or the entire time, figuring out food costs, making the operation of the Texas Star Party back to what it used to be and a bit more transparent to try to get people to come. They didn't have a lot of people showing up last year. So moving on. October 9th and 16th, trip to the fort. I appreciate these. I had to steal these off of Fred and Sandra Miller's Facebook. I'm not sure who had that out there. That looks like Bob Taylor's trailer, and I'm not sure how he managed to get that out there without talking to the people at the fort. But I see Mark, I see a few people, Fred and Sandra here. Looks like he had a pretty good time. These came from Alan. Really nice pictures of the fort. This is what the fort's all about. Hopefully these all clear out and you have a really, really good time. These kind of pictures are also here, and reports are here to try to inspire you to go. Also, pictures from the fort were really, really cool. M42, obviously, and Horsehead. It's a really good one of Horsehead Nebula. Really like it when people give me images. We got Al, looks like Stan, Mark, and Alan. Okay. Again, over here, Dob, this is the ruins out here. Really, really good and clear skies. All right, El Dorado, a lot of these courtesy of Doug. Got the two here. People that went were Alan and Karen, Mark, Al Mallory, and Doug. And I think that ended up being it for that one. That's okay. I appreciate it. I appreciate you getting the pictures nonetheless. November 4th, Star Party at UHCL. Stan, Doug, Richard, Justin, Mark and Hilda, George, David Brown, and Reed Klotzer. Thank you very much for doing this one. I know there's a lot of lights there to deal with, but I think the students usually appreciate it. Here with the scope, Justin with a C star. I didn't know you had a C star, Justin.
It's not my season.
Oh, okay. All right. Borrowed. I got it. All right. Samina, looks like Mark and Richard. The people having a lot of fun, which is what these things are all about. October 28th, Tuesday, Armand Bayous Nature Center did not work. We had to schedule that one because of weather that night. We were completely banjacked cloud-wise, and pretty much the same thing happened November 1st with the Sun and Moon event at the George. There were no photos. Leonard told me there were 200 people in attendance. They had a pretty good internal program, a few other things, but all three domes ended up running their cloud program, which basically means showing a lot of PowerPoints of pictures they've taken in the past. And the cow that jumped over the moon did not factor in any re-entry issues. So that's it for the Star Party.
Okay, so next month we'll be here December 12th, UH Clear Lake. We're going to do a series of short presentations by JSC members. Any of you who are presenting who have not given me your titles, please give me your titles so I can put an agenda together and know who's actually going to do it and who's not. We want to have the right amount of presenters, not too many, not too little. All right, door prizes. So I need the door prize bucket.
You gotta announce the.
We already did that.
Okay, so we're going to do two things tonight. We're going to do these special giveaways here, and then we're also going to do our normal door prizes. So the first thing we're going to give away is that telescope over there. And what I'm going to do, well, first off, give me a show of hands of how many people are actually interested in this telescope. More than one. Okay, so I'm going to write down a number here. Hold on. A number between 0 and 1. And so what I want to know is I want to hear your numbers, and whoever's closest to that number gets the telescope. I wrote it down here. And if you don't know that there's an infinite number of numbers between 0 and 1, you should not have a telescope. Okay, who wants to give me their number first?
You said 0 and 1.
I said, give me a number between 0 and 1.
There's only two numbers.
There's an infinite number of numbers between 0 and 1. And if you don't know that, you should not have a telescope. Okay, anybody that knows there's an infinite number of numbers.
0.72.
0.7. Okay, hold on, Leslie. Leslie, 0.72. Who else? 0.221. Jackson, right? Who else? Samina.
0.321.
0.321. Samina.
0.585.
Justin, 0.585. You want to try again now?
Yeah. 0.01234.
Okay, hold on. 0.01234. Ow. Oh, right there.
0.465.
Okay, 0.4685. 465. 465. What's your name? David. All right. Right here.
0.766.
0.766. Alan. Dad.
0.812.
0.812. Dad. You only get to see when you have kids, you're just dad. Nobody knows your name. Sorry. Okay. Anybody else? Right here. 0.001. All right. Any others? I hope not. That's enough. All right. Let me look. My number was 0.618034. Can anybody tell me what that number is? You all flunk. 0.618034. Okay, so hold on. Leslie.
Sweet.
I think 0.72.
Mm-hmm.
Yes, that's the closest one. Come on, Leslie. 0.618034 is the Fibonacci number. Guys, point Fibonacci. Thank you. There you go, Leslie. Way to go. All righty. Next giveaway is for the volume 1 and volume 2 of the Night Sky Observer's Guide. These are great books. So let me see a show of hands. How many people are actually interested in these? Oh, a lot of you. Okay, very good. All right. Now, I'm going to pick a number between 0 and 100. Okay, who wants to tell me a number first? Since I confused you so much last time. David. But that's okay. It's still between 0 and 100. What'd you say? What?
53.
53.565, right? Okay, excellent number, David. Anybody else?
45.
25. Oh, video.
45.
45. Thank you. Jackson. What? 82? Okay, Jackson, 82. Anybody else? Dad?
24.
24. Anybody else? Rick?
46?
46 from Rick. Right here. What? 33. Justin?
21.
21. Oh my goodness. Reed, I should have done this a different way. 57. Anybody else? Alan?
36.
36. Oh my goodness. Alan. Okay.
None of y'all got it right.
What? Okay, 93 from our vice president. Alan, what was your number? 36? Okay, hold on. Okay, Brandon is 93. Stan?
85.
85. Stan. Anybody else? Please, no more. Samina? 92. Samina. Okay, any others? I hope not. Any others? No, that's it, right? Okay, my number was 73. Ooh, Alan, Alan was 36, right? Who's the closest to 73? Man, there's nobody close to 73. Hold on a minute. 73. Stan was 85. That's like 12 off. 82. Oh, no. Yeah. 82. Who said 82? Jackson. Jackson, I think you're the closest one. Okay, Jackson, I'm bringing it to you, buddy. Okay. Last one. Dennis Webb's books. Animals of the Deep Sky. How many people are interested in these books? What?
What volume?
Oh, yeah, volume 1 and 2. Okay, you guys are okay. All right. Hold on. All righty. I need another piece of paper. Hold on. All right, here. Okay, let's see. We want to pick a number between, we'll do 0 and 1 again. All right. Who wants to go first? David?
0.565.
565, good number.
0.68.
0.68. John. Rick. 0.70. Rick. Stan.
0.35.
0.35. Stan. Dad.
24.
You like 24, don't you? What's the deal with you? The 24's up there, guy. Anybody else?
0.757.
0.757. That's a really good guess. Okay, let's see. That is Justin. 757. Okay. Anybody else? Ovidio.
0.82.
0.82. Ovidio. Anybody else? Samina.
0.57.
0.57.
Yeah.
Samina. Anybody else? Okay, very good. So my number was 0.7. Let's see. Rick had, what was yours? 0.7, right, Rick? All right, Rick, you got it, man. Okay, so we'll do a couple regular door prizes here, and then we'll get out of here. All right, so look at your door prize tickets, and first one is 250. Any 250s? Really? All right. Am I not seeing that right? No, 250. Okay, good enough. 256. Oh, David, come on down here. Okay, hold on. So, David, I have some astronomy things, but I also have this thing. Kind of cool, huh? I also have this thing. Oh, astronomy stargazing. Pretty cool. How old are you?
9 years old.
9 years old.
Yeah.
You know what? I don't know. This is really a good book, Dad.
Okay.
This is the best of the best.
Yeah.
Let me tell you, astronomy books. You want this one?
Yeah, I'll take it.
That is a good book. Thank you. See, he passed up the flashing blue lights. Smart kid. He went for the book. All right, good. That is my favorite, all-time favorite beginning astronomy book. It's excellent. I think it's the best book I've ever seen. Okay, 253. All right, Masood, come on down here, man. Oh, I know he'll want this. Okay. Maybe.
Oh, it's your choice.
Okay, no.
Whatever you like, I will have.
No.
Whatever you like.
I got discovering astronomy.
No, whatever you, I leave it to you.
You leave it to me.
Yeah.
I don't know what you like.
I know.
Would you rather have a book? Oh, I got a moon map.
Whatever you,
A map of the moon.
whatever you have given, I will like that.
Man, I never had anybody that's so flexible. You want some socks?
Give me some.
You want the socks?
Yeah.
Okay, these are. Oh, wait a minute. Okay, these are radio astronomy.
Oh, that's
socks.
great. That's great.
Okay, very
Thank
good.
you very much.
All right.
All right.
Thank you. Okay. Finally got rid of those radio astronomy socks. You guys see that? All right, couple more and then we'll be done. 269. Jackson. Oh yeah, that's okay. You can win 2 things. Stay there. All right, Jackson. I've got Discovering Astronomy, a book. I've got Exploring Amateur Astronomy. I got Spies in the Sky, about spy satellites. I've got I got a Stephen Hawking book, Black Holes and Baby Universes. Hold on. I got a moon map. I got a hold on. I got a flashing blue light. Stephen Hawking. All right. Hold on. It's coming your way. One more. Last door prize. Don't say we don't bribe people to come here. All righty. 255. David, wait a minute.
Dad's ticket. Yeah.
Dad's ticket. All right. Come on down. Okay, let's see. I gave you a really cool book. I can't give you that one.
Are there any astronomy socks?
Oh, I gave the last socks away. This thing is Astronomy and Stargazing. It's a pretty good book, pretty good pamphlet here about stuff.
Okay.
You like that one?
Yeah, I'll take it.
All right, take that one. That's a good one. All right, good. Okay, that's it. Thank you for coming. See you at Mod PCC next month. Oh my goodness. That was crazy. Let's see the 0. Okay. Where's the door prize tickets? Oh my goodness.